Okay.
Yeah, we can see it.
Okay. So sorry for the technical difficulties. I'm Ruigang from Shanghai Jiao University. So today my talk is from real to sim to real for autonomous driving and the robotics. All right. So there are lots of need for embodied AI in like a healthcare, robotic surgery, assisted living. The challenge is that they have almost zero tolerance for failures, right? You can't allow a robot surgery to cause any damages on the patient. And they're also needing service robots and the delivery, housekeeping. But the working conditions are very, very diverse. So everyone's trying very hard to generalize the BLA to be to be as versatile as capable as possible. Also in manufacturing, manufacturers are probably the widely use of robotics those days in welding, assembly, and pick and places. So many talk about successful rate, and I also want to mention one point that is efficiency. So in any modern manufacturers, and in any modern factories, everything has to be running on a beat, right? But look at some of our videos, like pick something, they are paying for this though. Okay, so that's the success rate and efficiency. And then also in transportation, robo-truck, robo-taxis, in the areas that I'm very familiar with. Similar to embodied AI in healthcare, they have zero tolerance for failures. And we all know that our large language models sometimes can make very gross errors. Right. So I think to make a embodied AI or a robot with embodied AI to be really effective, there are really two things that we have to keep in mind. First is breaking the upper bound, and the second is keep the lower bound. I think everyone knows how to break the upper bound. That is the scaling law, right? Applies has been very successful in large language models. But I really want to mention briefly as how we can keep the lower bound. I think this is not something that we typically as academia or researcher will talk about, but I think it's absolutely crucial to make our research, our papers into real product. It's how to keep the lower bound. Okay, so but today I'm going to talk about how to, and as academic talk, I'm going to talk more about how to break the upper bound. Okay, so I think the biggest issue for embodied AI research is, as you could imagine, data, right? Is unlike large language models that can use all the internet text for their data, the data for embodied AI is really very sparse. So to give you some examples, right? So in this is in autonomous the one way to use data is actually to get the real data. Okay, so in autonomous driving, the biggest open data set is from Waymo. It has about 600 hours of driving data. Some of them are annotated by humans. Some of the data are annotated by large models, in fact. And also in robotics, they also do gas run it. But look at those. We're looking at maybe a billion images versus 13 trillion tokens that are used in training the large language models. Okay, so using real data is going to be very costly, and it's going to be difficult to really scale up. So the other approach is obvious to use simulation, right? In autonomous driving, there's this Kala simulator that has been widely used. Also, there's the simulation for doing graspings. But the thing here, I attended my first robotic conference about 80 years ago. The first word I've learned is sim to real. The sim to real to gap is very big. So this is what I propose, okay? So, well, I think many people are doing this as well. So I think that a real to sim, and then to real pipeline is the way to go. So basically, it involves three steps. The first is real sim reconstruction, and the second is a simulation in the world model, and then we can so by doing that, we get both the realism in the real sim, also get the diversities get to also get the scalability that we can do in simulation. So that could greatly improve the amount that we can accumulate and get training data for robotics research. Okay. So I'm going to talk about some of my early attempts in this regard. And this is a paper we published in 2019, very old, but today's that. It's called the ADS, Augmented Autonomous Driving Simulation. So what we're doing is essentially we are combining the background from a real environment composited with a simulated car so that we can get photorealistic results and everything is annotated as well. So here's our AADS pipeline. So we got RGB images and we got LiDAR point cloud, and we also get segmentations, and then we process a number of steps in order to simulate the normal things. Okay. The first step is okay, we do semantic segmentation, and then we figure out what are the moving parts, and then we remove those moving parts to get a clean background. And then we also fit those moving cars, in particular those cars with a symmetric, with a semantic passing algorithm, and we also estimate the lighting to make it more realistic. And now with that, we can really simulate the car moving in an arbitrary way. Okay. So we're not going to, I don't have time to really go through those technical details. I'm just going to share some results and using a deep learning, a UNet-based impeding algorithm that we can really get some very nice impeding result. We are using a very classic image-based rendering approach to simulate virtual viewpoint changes, to simulate car movement from those four images. We can both interpolate and extrapolate different views. And then for flow simulation, we use a optimization-based approach. We got lots of data, traffic trajectories, and we use optimization approach. During initialization, we got our trajectory data, environment setting, and also the number of agents that we want to put in there. So the cost is that first, each agent should avoid collision, and they should also have a continuity, right? And they have direction control. Every agent is moving from direction A to direction B, and they also have some kind of attractions that naturally sometimes it will form as a particle system, and then we put those into our optimization framework, and then so that each agent can move freely and avoid the collisions. So by putting all those things together, we got the static background, we have the capability to change virtual viewpoint, and we have the capability to render simulate the cars. And then we got this capability, which we call the scan and simulate. So that's the data set. Okay, we do the semantic segmentation. We remove the objects and we fit the 3D model. And we do the realistic texture transfer. Now we can really move everything to anywhere. So we can put our cars into a new environment, and we can also simulate the different place and different flows of cars. It is, so we evaluated the data we generated, and we basically put our data with color and compared with color and virtual kitty, and then we use the cityscape for testing, and our simulated result can really improve the AP score. And we also did a LiDAR simulation, and you can see that our LiDAR simulator is more sophisticated and more realistic looking, and it also helps improve the detection accuracy on kitty. And here we are doing I personally believe that probably we're one of the earliest work on end-to-end simulation back in 2019. So let's look at those three scenarios. And in the first scenario, so right now there's really no, this is the original thing, there's no vehicles, so anything moves. And I'm sorry. And then we can, sorry. Oh, sorry. Yeah, we need to let it play longer. Okay, now this is three scenario. In the first scenario, if the car move forward, it will stop because there's a car right in front. And then if the car moves right, and then it also stop, it also fail. And so only the last scenario that the car first move to the left and then move back to right, then it's able to pass this set of vehicles. So that basically set up the environment for reinforcement, reinforced learning. Okay, now fast forward to now, one of the most popular items, one of the buzzwords in 3D vision is actually 3D GS, right? 3D GS can significantly improve the view synthesis quality and has been used from 3D reconstruction to 3D modeling. The problem with 3D GS when applied to autonomous driving is that it is really unable to really change the viewpoint. The 3D GS is great at interpolating between views, but when you think about autonomous driving, you only scan the road once. So whenever your viewpoint is deviating from the original viewpoint, the 3D GS result deteriorate very, very quickly. Okay. So how can we do that? And so we're effectively combining 3D GS with diffusion-based image generations. So what we're doing here, essentially, we use the classic we reconstruct the 3D GS as usual, and then we change the viewpoint and to create synthetic images that are, for example, moved to the left or right of the original viewpoint. And those images have artifacts, and then we put into a video diffusion. At that time, we were using a UNet, and we actually have a better version now. Anyway, we use those diffusion-based image repairing algorithm to generate refined images. And from those refined images, so we put them back into the 3D reconstruction process to create better images, to create a better 3D GS representation of the environment. And so you can see this is our result. The first is the original view, and the middle one is something called straight Gaussian, and the last one is our result. You can see in particular in the ground, the image has much higher fidelity. Okay, and then we also computed the PSNR and the SSI number, and it got some quite significant improvement. And we also tried our algorithm on a nicely seen and using our approach and plus some of those video diffusion, more sophisticated video diffusion framework, and it is able to get really convincing images. I should apologize for some of those blocking artifact. It is not due to the video diffusion model, it's due to the display. I think somehow on this particular computer, sometimes this artifact that shows up. So this is the original image. This is turned left by translating by 1 meter, 2 meter, and 3 meters. So you can see the results are quite consistent. Okay, so those are about autonomous driving simulation, mostly about image generation. And so this for I think the biggest AI versus embodied AI is actually the physical interactions. So from there, the real sim to real pipeline need to have some upgrade. So what's the upgrade? Is the physical properties. Okay, we need not only reconstruct the 3D geometry, we also need to reconstruct the geometrical properties of the real world, and then we can simulate them do simulations. Okay, so with that, I'm going to represent some of my latest work for government manipulation, which we call this is something we have just submitted. So it's called RG Bench. So it has 3 components, and the first is a industrial quality class data set, government data set, and the other is a very fast simulator, a government, we call it government dynamics. And we also define the several tasks such as grasping, fleeing, and fold, very typical operations to handle clauses. Okay. So let me first talk about our government dynamics. Okay, so compared to the old existing simulations, we have some very unique properties. So if you use a continuous FEM method and with an isotropic model to directly manage stretch and bend response, so it could have more accurate wrinkle capturing, and we actually measured the close physical properties using ASTM international standard. So we put our clothes on those standard measuring machines. We measure its stretch, we measure its bend very accurately to be physically accurate. And we also implemented a GPU native implicit solver. So the dynamics are entirely solved on the GPU. Okay. We also use some preconditioner to rapidly accelerate the convergence time. We are also probably the first to leverage the NVIDIA RTX hardware, and in particular, we had designed a robust untangling algorithm for robotics, in particular to ensure that when your gripper is clipping on a piece of glass, it will not penetrate. Okay, and so let me show you some results that we got from ISAC when we are changing some of those parameters, that you can see that it is not very robust. Okay, so then we compared our simulation with Mojuko, ISAC and the PyBullet, and we are essentially about 3 times faster than ISAC. Okay. And also the initialization time is reduced by 90%. So that's the average initialization time. They are in the order of minutes. Okay, look at Isakasim and Mojuko and PyBullet, and we are in the order of seconds. And here is the average step time, and the y-axis is the step time, the x-axis is number of cross vertices. And the lowest one is our garment dynamic. It's about 3 times faster than this is Isakasim. And this one is Mojuko. Mojuko failed to load when the number of vertices exceed the 20,000. We also compared the accuracy through of a number of models we captured. We have some real closes, and then we digitize them with physically accurate measurement and modeling. And then we compared the simulation result with the ground truth, and you can see that the shepherd distance that we basically get and for almost every measurement, every experiment, we get the most accurate result to the real. Okay, so let me show you some. I think there's some videos I can show you. Oh, I'm sorry. Okay, so not the really videos. Sorry about that. So so this is our. Oh, actually, there are videos. Okay, just didn't play. So this is our method. And this is from the next one is from Isakasim. Okay, that's the folding result. And this is from PyBullet. So PyBullet is entirely failed. Okay. So this is the comparison, and then let's talk about the data set. The data set including 2,000 public government assets that we gathered off the web. It also includes 4,000 plus of industrial level government assets with over 10 different materials and and over 100 different subtypes. Okay, and so you can see that our models include not only t-shirts, it also include the skirt and very different diverse set of real garments. Okay. So about to close, okay, looking forward. So I started my career as a computer graphic person, and then during my PhD, I got into computer vision and to do 3D vision. That's really my core area. And if you combine robotic lasers and the intersection of those is what I believe is embodied AI. So basically, computer vision is able to understand, reconstruct and model the world, which I call the virtualization, right? For computer graphics, what it can do is that it can really predict, okay, either through a physical-based method or using some of the more latest machine learning approach. And what the robotics bring to the picture is really interactions. So with interactions, and now we close loop, right? We call it embodied AI. I believe the key concept of embodied AI is that the learn through exploration. So you have to have this interaction component in there. So there are definitely a lot of research opportunities ahead. The biggest, as I mentioned, is the data issue, okay? And many are talking about, okay, can we really learn some policy from internet videos? It's a big question about that. And what, should we use imitation learning or use simulation? Okay, which is the way really to scale up, which is the real way to scale up the embodied AI data that we need, okay? For me, my background in computer vision, so I always find that pushing the boundary of computer vision with large language model is very processing. I believe in one of the previous talk, people about already talking about, okay, how can I estimate the physical properties, how heavy this is, what's the friction through visual means. Finally, novel system architectures. So many talk about decoupling decision and actions, fast and slow, and is end-to-end really the answer to many of our robotic issues or robotic questions? My guess is that they are not really. All right. And okay, so that concludes my talk, and thank you for listening. And I do have here's my contact information, and I'm definitely looking for PhD students, faculty, young faculties. I'm starting a new center at Shanghai University, so definitely looking for collaborations, either locally or globally. Okay, thank you for your attention.
Thank you, Ruigang. Do we have any questions from the room?
I don't think I've seen any so far.
I can ask a question if no one in the room is asking a question.
Okay, maybe we can ask. So I'm going to host my own session. Okay, and you can see some audience in the background. So maybe we can start from you first.
Yeah, okay. So my question is that I see you have a work like using diffusion model to improve Gaussian spotting. So I wonder if you see any limitation of that work, because my imagination is that you can do novel view rendering from like 1 meter from the original training view and then use diffusion model to improve the image and then improve the Gaussian spot. So in my imagination, by doing this, you can keep improving it, like doing novel view synthesis from like 1 meter, 2 meter, 3 meter, and infinity. So do you find any limitation by doing this, or it is possible to build a really good Gaussian spot representation by combining diffusion model and Gaussian spotting?
I think first we haven't really go very far. So I think so far we're. I saw you guys hear that. Okay, so the question is that can you really use the diffusion model to greatly expand the range for 3D GS reconstruction? Okay, so we have not tried anything beyond 5 meters or so. So with this 3 to 5 meters, it works great. And if it goes any further, my guess is that the 3D consistency cannot be guaranteed. the viewpoint is probably too large. I'm actually very interested in trying some of the latest models from ChatGPT Sora 2 or those VO3, which all claim have a great temporal 3D consistency. I'm eager to try those, but I haven't. One thing we also noticed that the 3D LiDAR really helps with the 3D LiDAR as seed for reconstruction, can really keep the majority of the structure in place. And diffusion models are really, really good at filling in the blank. And but if there's something that are already distorted, like if the window becomes zigzag, then it really does it is not very good at fixing it. So by combining 3D data, in particular for autonomous driving scenario, usually there are 3D point cloud and they're accurate. We found that having accurate 3D, even in a sparse way, is much better than have dense depths, but with lower quality.
Yeah, I think that's really similar to what I found. So my work is about like using LiDAR to improve the Gaussian
Yeah,
spotting.
exactly.
And yeah, it show that it provide like better overview synthesis, but it still cannot like fill in the hole in the unobserved region. So I think diffusion model is something that can like combine the advantage. Yeah, by combining advantage of like LiDAR and also diffusion model can improve the like a digital thing reconstruction and Gaussian spotting reconstruction. So yeah, I think that's what.
So I think there's an audience in the back.
Yeah, thank you for the wonderful talk. And I really like the words you presented. So I want to ask in the beginning, because you mentioned there's two directions, right? One is to push the upper limit, one is to keep the lower bound. So I wonder if you can share some insights or elaborate more on, for example, the works you presented or the future plans you have in related to the direction of keeping the lower bound.
Okay, that's really a very good question. And I can tell you what industry are doing, in particular in the autonomous driving industry. And you can see that many companies, autonomous driving companies, are claiming to have those VLA plus VIO models on board. Okay, I'm not sure if VLA is really necessary for autonomous driving. And on the other hand, I think almost all of them, as far as I can know, they always have a classic pipeline that using a white box approach. So basically, it's a rule-based approach to make sure that the decision or the trajectory generated by the learning system will not violate some very basic physics laws, such as collision avoidance. So this is what industry is doing. And also there's something called safe reinforced learning. I think it's getting popular those days. But from industry perspective, basically, we really have two systems. Excuse me.
Ruigang, if there is no more question
Yeah.
from the audience,
Yeah, okay,
Mr. Tong will introduce the next speaker. Yeah.
Yeah, okay. So so that's the basic question. So you have to have a rule-based system to keep the lower bound.